Hello everyone. Welcome back to ComSci Connection. It is good to have you. It is good to be back. It has actually been quite a while since I've done a video, and I thought what better than to jump head first back into ComSci Connection videos than to go straight to graphs, right? Well, hopefully if you're watching this video, or if you're thinking about watching this video and learning about graphs, you won't dive directly into this video unless you're already pretty familiar, or at least somewhat familiar, with some of the previous forms of data structures, such as linked lists, or maybe at least trees. Trees kind of derive from linked lists. But if you're capable of and understanding and comfortable with trees, then you should be just fine with this video. Now, what I'm going to do is talk about what a graph is in terms of computer science, and basically show you an implementation of a graph that I've made myself. Now, speaking of that, I probably should add a little fancy author tag here, because this is my own code, and you will notice that there are not you may notice that in a Java API libraries, you're going to see lots of implementations for, for various types of lists, sets, trees, all these kinds of things. I mean, you could pretty much use the Java library for just about anything. But to my knowledge, and to the knowledge of the people that I've spoken to about the topic of graphs, there are not any actual solid implementations of straight graph in the Java API libraries. So it's something that is really, it's something you want to develop on your own. And I think one of the reasons for that, is that a graph is a really specialized data structure, and what a graph contains in terms of its smaller components is really specialized based on what you're actually trying to do with it. And so I think that's really has a lot to do with why you're not going to find a standard graph library in the Java libraries. But I digress. I'm going to go ahead and just get started into what a graph is. So a graph is not the same thing as what you would typically see in mathematics. We don't actually have, you might think of maybe as a 2 or even 3-dimensional array, maybe with different indices that you could place items. And while it is possible to build a graph that represents something like a mathematical graph in that sense, it's not really the same thing at all. If you're familiar with linked lists or trees, you're familiar with these relationships that certain nodes or vertexes can link to other nodes or vertices that may have certain relationships with each other, or may relate to each other in some way. And this is very similar. Now, with a linked list, a lot of times you really are just combining a whole bunch of components together. You really have a simple traversal mechanism, and you just kind of follow that path. Trees get a little more complex in the sense that you can have relationships of parent and child. You can have something like a binary search tree, which relates left side and the right side relate to the parent with certain rules or regulations. You can even have what I still call a tree, but some people will pronounce it trie, which might be a tree with multiple children of any number or any relationships that might be based off of that. And there are many uses for these types of data structures, but a graph is very similar to a tree in that sense, where you can have lots of relationships between any given node or vertex, as I will refer to it through the rest of this video as. So there's going to be a couple things that you'll see throughout my code here that I'm going to make sure that I address before I begin explaining what's going on in my code. One of the first things you're going to notice is I am using generics for my graph, so you'll see this type T, and if you're not familiar with generics, I feel like you still be able to understand and kind of process what's going on in this video, so it's not necessarily important, but for you to understand that, at least to understand this video. But if you feel like you're not following what's going on, or the relationships between data types in this video, then I would definitely recommend that you look up your own information, look up or do some research into generic types in Java, or check out one of the ComSci Connection videos. Shameless plug there. So that's the first thing. And the second thing I'm going to mention is that you'll notice right off the bat that I have defined an enumerated type called type, and I've given it two options, either undirected or directed. Now, when it comes to graphs, as I said, it's kind of like a tree in that you can have relationships between certain nodes. Now, a tree can actually connect, maybe a parent node to the child node. And let's take binary search tree, for example. You would have a left node, or left child, and a right child, both of which may have parent pointers that allow you to get back up with the tree. In that sense, if we had the same relationship between three nodes in a graph, it would be what's called an undirected graph, because you could go down, you could go back up. There really isn't so much down and up in terms of graphs, but you can go, if you can go from A to B, you can go from B to A, and that's just a given with an undirected graph. A directed graph is it's the opposite. It's very intuitive. It is, if you can go from A to B, you cannot necessarily always go from B to A. Now, could you specify the ability to go from B to A? Yes, absolutely. But the relationship there doesn't automatically mean that you can go back and forth. And the example that I'm going to use later on in this video will be a directed graph. So I just want to make sure that I specify that. So actually, with that being said, I'm going to go ahead and pull up a picture here that I made in lovely MS Paint so you can see the quality that really went into this. But this is actually what a graph kind of looks like, or how we would represent a graph. So you'll notice I have some nodes here with different letters or different data contained within them. And although they seem kind of in order at first, I will specify that I didn't really make them in a specific order. So you're not really going to see an alphabetic pattern or anything like that. And try not to focus on those small details. Let's just look at the relationships that we have between the different vertices. So I have obviously A here, and as I said, this is a directed graph, so I've drawn arrows to indicate that A can traverse to B. B can traverse to C, D, and E. C can traverse to H, but not back to B. Similarly, B can't go back to A. H can go to F. F can go to I. D can also go to F. B can go to D. You see these relationships, and I hope this graphic has made it pretty obvious what's going on here. This is what we would call an unweighted directed graph, or it's essentially a representation that I've drawn of it. Could you draw this in any number of ways? Absolutely. As long as those relationships stay the same, that's perfectly fine. But I feel like the way I've drawn it here helps to encapsulate the idea that I'm going to get across throughout the rest of this video. So this is, as I said, unweighted directed graph. The directions are specific. You cannot go backwards once you've gone forward to a specific node. And you'll notice that every one of those arrows, while some are longer than others, they don't have any real values. They don't have any real weights, as we would call them. So I'm going to go forward to another picture in which I've given the the edges weights. So to clarify the terminology a little bit, each one of these nodes, or vertices as I said I would refer to them as, are containers for data. And it has two things essentially within it. It has its current data, or what it stores, and then it also will have a list of edges. And an edge is simply just a connector between one node to the next, or vertex. So an edge allows you to traverse from the vertex you're currently at to the next one. And in a directed graph, an edge will typically imply that you can only traverse that one direction. So as you can see here, these edges do have numbers attached to them, or weights. They have a specific value which determines how difficult it might be to traverse that way, or to traverse that direction, to go from B to C, or maybe how I want to handle that relationship between, say, B and C and B and D. They obviously have different numerical values there, i.e. different weights, and therefore there's some kind of relationship there that I want to make sure that I imply. Now, just as an aside, you will see other graphs can also have weights within their nodes, or their vertices. This example that I've chosen to go with does not have weighted vertices. So you will just see a simple vertex containing a list of edges in which you can use to traverse. Then those edges themselves have weights, but the vertices in this example do not have weights. So this, as kind of a preview into what we're going to go into, try to keep this picture in mind, but I will refer back to it multiple times. So let's go ahead and look at the code. Now, I've defined a graph of type T, which means that I'm going to, at runtime, I'm going to associate a certain object type with this graph, and that type will be decided at while I'm actually compiling the code and creating a graph for the first time, and then the entire code for the graph will kind of behave with that data type. So not to be confused with my enumerated type here, I've created a private variable to represent that, and then the default constructor just makes it an undirected graph. You'll see that I can also pass in one of my enumerated types here and construct a graph of that type. Now you'll also notice that I've chosen not to store a head pointer or maybe an initial or starting point node, and that's just a choice that I made personally. These kind of things, as I said, you can implement them however you want, so that's just something that we'll move on from. Now I'm going to skip past these searching things, and yep, searching, and then this is an algorithm I'm going to cover in another video, not in this one, and we're going to go ahead and just look at the components. Now you'll notice I've created a public static class called vertex, and this is the same type T that I referred to as a graph, or in the graph. And you'll notice that I'm going to store one T type, or one object of type T, that's going to be called data, and that's a private instance variable there within the vertex class. And then, as I said, I'm going to store a list of edges for that vertex, so that vertex knows which edge it can, or which edges it has, or which relationships it has with other nodes. Now, as a quick preview, I will show you that I also have a public static class edge. I'm not going to focus on that quite yet, but just so you can see that this is a list of edges that I've created. So a list of edges is the compile time type there. The runtime type will create an array list of type edge, which will initialize the edges list of type edge, type T. So the basic constructor here takes in an object of type T, which will be that type at runtime, and we'll store that data in our private instance variable data, and then initialize the list of edges. So that's just I like to use this dot. It really doesn't matter. This in this situation is kind of a small aside. It does matter since data, the local variable, has the same name as data, the instance variable. You do need to imply this dot data to refer to this current object's data variable. But since edges was really the only instance, or the only possible option for the reference edges, it had to refer to the list. But I still like to put this dot just as an ease, kind of something that your eyes adjust to and just see it that way. So I've got a method here which returns a Boolean value, which will add an edge to the given vertex. This will basically check to make sure the edge is not already existing within our list, and if it does exist, it will return false. If it does not exist, it will go ahead and add it and then return true. A pretty simple method there. Then I've got another version of the add edge method, which will actually just take in a vertex and a weight, and then it will actually go through all the edges and check to see if the vertex already exists in the list of edges. And you can just kind of ignore this because I haven't really talked about the edges too much, but essentially you can assume that this is checking to make sure that there is not an edge that exists that has this given vertex as the direction that we're going. So yep, so then I'm going to go ahead and add a new edge, which I've constructed using this current vertex, and then the weight, or the vertex that I'm currently given as as one argument, the current vertex that I'm residing in when this code is being executed, and the weight that I was given in this constructor. And then I've got a couple simple getters here. This is going to return the list of edges, and as you can see, it's just a simple getter, and then also a getter for the data. Pretty simple class there. I will go ahead and collapse that for now because we don't need to refer to it any longer. And now, what did I just do? Oh, I closed the Boolean method there. I meant to close the class. shrink our code a little bit. All right, now we're going to take a look at the edge class. So as you can see, I've got a weight, which is a private instance variable referring to the weight of the edge, which is these numbers here, these values. And then I've got a to vertex, which is where this edge will take us to in the direction. I've got a from vertex, which is where we're coming from. And then I've got a basic constructor here, which just sets up these relationships as given. So as you can see, to, from, weight, if I refer back to when I constructed this edge up here, I said I'm going to go to vertex, the given vertex that I'm trying to add the edge to. This is back in our vertex class. And then I'm going to go to this vertex from this vertex, and then the edge that I'm adding will have the weight that's given to us in that method. So so that's the basic constructor there. And then I've got a simple getter, which will get the vertex that we were going from. I've got a getter that will get the vertex we are going to, and then I've also got a getter that will return the weight of this current edge. And now I do have another class in here called a vertex weight pair, but we're going to ignore that for now because it doesn't apply to this video. I will cover that in Dijkstra's algorithm in the next video that I do. So let's step back up actually and talk about a few things. No, actually, that is our basic intro. I am going to go over some of the searches or the traversals of the graph here within this same video, but I want to refer back to this graphic for a second to kind of wrap your head around this. So again, this is what we are going to be constructing within this video as an example, and we'll follow this exact same graph as you see on your screen right now throughout the rest of this. And in order to implement that, I have created a class, a main class here, and I've just kind of brute forced some graph vertices and also some edges. So as you can see, I kind of gave them silly names, but I've created a new vertices of type character, which is the wrapper class for car, of A, B, C, D, E, F, all the way through K. Gave them kind of silly names, and then I'm adding these edges, and you can just trust me that I've already verified that this is correct and does match our directed graph illustration here. So I've added edges from A to B, B to C, D, and E, E to K, so forth and so on. So I created this relationship, and I've also given them the values of the same weighted values that I've drawn on this graph here. So let's talk about traversal. So what are graphs good for? Why would I set up these kind of relationships, and why would I want to put any kind of weights on the graph? Well, and it's an interesting question. These types of relationships can represent a number of things. They could represent maybe a pathfinding algorithm that you might want to get from point A to point B. Talking GPS systems, maybe a networking algorithm, like saying, oh, I'm at this server right now and I want to access some information that's on some server in some other part of the world, and how do I get there? What is the path that I'm going to need to do that? And those are just a couple basic examples, but great ones. And these are the exact types of things that graphs are amazing at. You wouldn't really have any kind of a linked list would be a horrible way to implement the World Wide Web, right? Why would you do that? It would be the most horrible, inefficient type of data structure to use for something that complex and intense. So for now, we're going to ignore the weights. And actually what I'm going to do is pull up an example. We're going to go through depth first, yes. So we're going to go through two different traversal types. There are two main ones. There are depth first and there are breadth first traversals for graphs. These are the two main ways that we can traverse through all of our nodes. And I think what I'm going to start with here is depth first. So I'm going to go ahead and pull up a picture here showing kind of what the pattern of a depth first traversal is going to be like. So what I will do is set up this. So I'm going to call a depth first search on the graph using the starting node A. And that is right here. So public void depth first search. I'm not really searching for anything, but I am going to traverse through, and then this is basically just going to print out all of the information or the data contained within each of the vertices, and we're going to see how this algorithm works. So basically what it does, or what the basic idea of this is that we're going to start with our given vertex, and I've created a recursive method because the best way to do a depth first search is recursively. We are going to visit one node per recursive call and then essentially traverse through every one of its edges that are connected to that vertex or node, and recursively iterate through those, or I should say recursively traverse through those edges to get to those vertices on the other side. So we'll take a look at this code first, and then we'll kind of step through it. So first thing I'm going to do is call my recursive method on the starting node with a new set of vertices. Now you'll notice here, obviously I'm kind of giving away what that's for, but it's a set of vertices that is our visited set. Now why would we do that, right? Well, the answer to that is pretty simple. If I have this directed graph, and even though my directions are implied that I can only go a certain direction, and you say, well, once you go to B and then C, you can't go back to B, right? Well, that's correct, but it's still a good idea to keep track of the nodes you have visited, because if you were working with an undirected graph, you could go back, and you would want to avoid that. It's actually called a cycle. And B, if you were to traverse down A, B, C, H, and F, and then from F to I, then later on, when you visit node D, you'll notice that there's an edge leading back to F. Well, what if, just humor me, that the F had another edge connecting back to H, and H had another node connecting back to C, and C back to B? You could actually create a loop there, just infinitely tracking through. And even though that's not the case in this graph, you could still visit F and I multiple times, which we don't want to do. So that is the reason why you need to keep track of the nodes that you have visited, or vertices that you have visited. I should just call them nodes because I keep messing it up anyway. So nodes is actually what I'm used to, but vertex is what I called it for the purpose of this code, and that's really what I should be saying, but I'm going to use them interchangeably. Just, I guess, get used to it. It's going to happen. So we're going to go ahead and start out by retrieving a list of the edges for the current node that we're at. So you'll notice I've sent start in as the first argument to the first recursive call to our depth first search, which will be taken in as a vertex called current. So let's go ahead and use that method called getEdges to return the list of all the edges that current has. Now I'm going to go ahead and visit the node, printing out the data, and then I'm going to add that to my list of visited nodes. That way I will guarantee that I won't ever visit that node again, because at this point, as we know, recursion is essentially going to pause at this stage while it traverses down a recursive path, going through each neighbor one at a time until all the neighbors down the path that we've chosen to go have been visited, and the recursive trail falls back until we've returned to this specific method. And if I visited any nodes during all that time, I want to make sure that I keep track of that so that I don't visit them again. This will all become very apparent as I step through here in just a few moments. So this is a for each loop. I'm essentially saying for every edge in my list of edges, then I'm going to create a vertex reference called next, and that reference will refer to the to vertex, or the direction that we're heading from our current vertex, or the current edge. I'm going to get the vertex that I'm heading to, and I'm going to store that as next. First thing I'm going to do is make sure that I haven't already visited it. So I'm going to ask my list of edges, my set of vertexes here, have I already visited next, this vertex that I'm referring to as next? Is it contained within this set? If it comes back and says no, then I'm going to say, or it'll say false, I'm going to say good, turn that into true, go ahead and call this method, which will recursively traverse further down this list. So let's take a break from looking at the code, and let's think about how this is going to work. So A traverses to B. Now B has three neighbors, C, D, and E, and we don't really know which one is going to get visited first, and the weights really don't matter in this sense. Now it's going to depend on a number of things. How am I storing those edges? Well, in this case I've just got a simple list. How am I keeping, what order were those edges added, or what vertexes were created first? A number of questions you might ask, but for the purposes of this video, it's going to be pretty simple, just left to right. It's the way I created the graph. It's the order I created the edges that lead from vertex to vertex. So as we're going down this list, B is going to have three edges connected to it. So we're going to have to iterate through each one. But as we know, the first edge is going to create a recursive call which will traverse from B to C. Now, what's the next step? Am I going to go from B to D? No, because currently the stack trace is going to show that now C is going to be considered the current node, and it's going to get a list of its edges, and it's going to visit that edge, and then it's going to, or visit that vertex, I'm sorry, and then it's going to add that to our list of visited vertices, and then it's going to go through each one of its edges, and you see where this is going, further traverse down that path. So in fact, even though we're still waiting on D and E to get visited, we are not able to do so until the entire path or the entire recursive trail has fallen back from this current recursive call into C. So the simple answer is the next visited node will be H. From there, obviously we know that we're going to go ahead and just go to F. And then from here, we're going to go from F to I. Now at this point, I doesn't have any edges connected to it at all, so the recursive trail will fall back. It simply will say for each edge in edges, which edges is an empty list, so the code will skip down to this line, it will exit the method, which will fall back onto the previous recursive call. And for simplicity here, oh, I am apparently, no I'm not. Alright, let's go ahead and step into this method and actually watch this happen. So I do hope you can read the variables section here. I tried to make the text larger, but as I increase the size of the text here, as I did down here, it just gets cut off by the size of these variable blocks or whatever. So it gets kind of difficult, but just bear with me and I'll try to spell out what's going on. So I don't need to stop there. I'm going to go ahead and resume. We're going to step into our depth first search. We know that's going to just call recursive depth first search on that same starting vertex given a new hash set because we haven't visited any nodes yet. Let's go ahead and step into that. We're going to return a list of all the edges from our current node. And our current node has a list of edges which is of size 1 because this is A to B. So let's step back, A to B, size 1. So we're going to go ahead and print out the data for the current node which we're at, which is A, as you can see, and then we're going to go ahead and add that to visited. So visited here, you'll notice is a map, and that map is, or it's a hash set. The hash set contains key value pairs in the form of a map. Little aside, but we're going to go ahead and add that, and you'll see that that graph vertex has been added there. And if I were to go down and select current, or up and select current, you'll notice that it's going to be the same address, 78AE82. So that is the set of our current visited nodes. I won't dive into that too much more, but from here we're going to go ahead and say for each edge in edges, which there's only one, we're going to get the to edge, or where are we going, and then we're going to say, hey, let's just make sure that first of all that edge or that vertex is not already contained with our visited one. Well, if I look at the reference here, close this and look at next. Next is going to refer to a vertex at this location which has data value B. So we know correctly we are going to traverse into B. We know we haven't visited yet, so it will execute this loop and I will recursively fall in. Now before I press the step into button, notice that I've got a graph dot depth first search and then recursive depth first search. This is the first recursive call. It's the starting point of our algorithm. So as I step in, you'll notice that this stack has been this method, which has been now created a new recursive call, is still on the stack, and it's still sitting here as the green highlight indicates that it's waiting on that method to finish, or that call to finish. oh, excuse me, it's getting the 2 vertex first, so I step into here. Yeah, I'll just set a breakpoint there so in the future I don't have to go through that step. So you'll notice now that I've got this initial recursive call that's sitting there waiting on the new recursive call to finish. So I can select our new recursive call, and we're going to follow through the same pattern. So we're going to get our list of edges, we're going to print out the data for the current node, which is B, and then we're going to add our current vertex to the set of visited nodes, so we guarantee we don't see it again. So at this point we are, nope, we're here. We are here. Okay, and then I'll kind of speed this up because I think you should be able to see where we're going. So let's get the 2 vertex, let's make sure we don't contain it. And you know what, I could have just put next here. Actually, I should have put next there, but I'm not going to stop it now to go through that because I've already stored the 2 vertex. So I'm calling that method again here and here. I could just put next in there, but whatever. So we know we haven't visited C, and if I look at next here, I can expand data and you'll see the value is C. So I am actually currently working with this edge here, and as I recursively traverse into that method, you'll notice that now the current node I'm at, has data value C. So I have done this. So as I step down, I'm going to get the list of edges, I'm going to print out the data. Oh look, C got printed to the console. I'm going to add that to my list of visited edges. I'm going to go through each visited vertices, and I'm going to go through each one of its edges, get the next vertex that we're heading to, make sure it doesn't contain it, recursively call. So now I'm at this point, H. So now we should see H get printed to the screen. Indeed we do. We should add that to our list of visited things, go through each edge, yada yada yada. We know that H only has one relationship with F, so we know that hasn't been already visited. So we will recursively step into that. So now you can see current data value is F. So we are at this step. And then now I'm going to go through this, print out F, visit that, or add that to our list of visited vertices, go through each edge, get the next edge, make sure it doesn't contain it, and then recursively call it again. So now you'll notice current data value is I. We are at this step, exactly where we were, where we said we would be. Now you'll notice on the left I've got all of these items on the stack, and each one of them is a graph.recursive depth first search. And each one of these, if I click on them, I can see that it is still the current node in that recursive call is A, B, C, H, F, and then I. I've already visited all of those except for technically I, but that's the current one that I will visit within this recursive call. So I just want to make sure that you understand that each one of these, while some of them, mainly B, do have additional relationships or different additional edges to traverse, they cannot do so until everything has fallen back to the point of which we are at B. So let's go ahead and do that. So we're going to go ahead and we're going to watch this current recursive call is going to get a list of current edges, which is empty. You'll notice size is 0. It's going to print out I because that we're visiting that node. We're going to add it to our list of visited nodes, and we're going to say for each edge in edges, which is empty. So as I press step over here on this very last brace, you'll notice that this top recursive call, which is at line 64, the only one which has advanced past this line, is going to fall off the stack and disappear. Bam. Now where are we? We're back at data value F. We are back at this call. Well, I, or namely more specifically the edge from F to I, is the only edge that's contained within the list of edges for F. So we know that as we go back to this top line for each edge in edges, we're done. So again, if you'll watch here, this recursive call, which is traversing the value of F, is going to fall off the stack. Bam. Now we're back to data H, back to this point. Well, again, there's only one edge in H, so this will fall off the stack. Bam. We're back to C. Again, only one edge, so it'll fall off the stack. Now we're back to B. So what's going to happen next? I think it's pretty obvious at this point. We know that we're going to go down the next path, which will lead us to D. Then D will lead us to well, it could be G or F, but we know what about F? it's already been visited, right? So let's take a look. Let's watch that happen, because I think that's a good thing to illustrate. So we are in B currently. We are at this step, and we're going to go through each edge in B. Well, the next edge, if I look at what just got added, or what just got referred to as next, is data D. So I am correctly traversing to this point, or I will. It's going to call a recursive call because I haven't visited D yet. And D has a list of 2 edges. I'll look at the list of 2 edges. I've got 2 items in here from D to F, and from D to G. So from D to F, from D to G. So if you can see in our element data here within our list of edges, the first element we're going to attempt to traverse to is to value F. So what's going to happen here is we're going to print out the value of D as we visit the node D. We're going to add that to our list of visited vertices, and then we're going to go through each edge in edges. We're going to make a reference to the next vertex which we're going to visit, which is data value F. Well, guess what? F has already been visited. It's already been contained. You saw this coming because I stepped forward on our fancy MS Paint demonstration, and you saw that it's going to check to make sure that visited doesn't contain next, which in fact it does. So as I step over this line, you'll notice that it's going to go back up to line 56 for each edge in edges. And it does. There's no need to traverse back down this path because we've already done so. So we're going to ignore that path and continue on. So we're going to make a new reference next, which will be data value G. And it's exactly what we expected, exactly what I revealed by stepping forward on my fancy MS Paint image. So we will recursively traverse into depth first search again with the current vertex having the data value of G. So we are at this step. So obviously we're going to go through each node in G, which only has one edge, or each edge in G, which only has one edge. Visit G, print it out to the screen, add it to our list of visited vertices, go through each edge in edges. We're going to have one edge, which next is going to have the data value of J, exactly as we'd expect. So we're going to recursively visit this one. So we are at this step now. Now, blah blah blah. We're going to get each edge in J, which is of size 0. We're going to visit that node. We're going to print J to the screen. We're going to add it to our list of visited nodes for each edge in edges, which is empty. So nothing's going to happen. So this recursive call is going to fall off the stack. Then G will fall off the stack because there's nothing left. Then D will fall off the stack. As you can see, I'm in D. It's going to fall off the stack. And now we're back to B. So obviously we know where this is going to go from here. We're back to value B, where we still have one more edge to traverse, so we're going to refer to our next edge to traverse as the edge which will lead us to vertex E. We're going to make sure it doesn't contain that, which of course it doesn't, and then we're going to recursively traverse to E. So at this point you really should be getting an idea of what's going on. We're going to visit E, we're going to go through each edge in E, which is only one. We're going to make sure it doesn't contain it. We're going to recursively traverse. Now we're at this step. And then lastly, we're at K. K is going to be visited. And then we are going to go through each edge, which is only one. We're going to make sure it doesn't contain J, but guess what? It does contain J. So we're not going to go through J again. It's going to fall back. Well, there's only one edge in edges to visit, so that loop will terminate. That recursive call will terminate. We're back at E. E only has one edge, so that loop will terminate. A recursive call will terminate, falls off the stack. We're back to B. B has visited all three of its edges, so it is going to exit its loop and then fall off the stack. And now we're back to current node, or current vertex, being the one with value A. Guess what? We're done. You notice there's two vertices here, or edges, excuse me, which didn't get traversed, but that's okay because we still visited those nodes, and that's a perfectly fine example of a depth first search. So as I press resume and exit out of my thread, you will notice that I have visited the edges all in order A, B, C, H, F, I, D, G, J, E, and K, in that order. So that is depth first search done with recursion. Now I know this video is probably getting pretty long, probably a lot longer than I intended for it to be, but I am just going to go train right on ahead into breadth first search, because after all, it's a video. You can pause it, you can go get food and come back later, and I don't feel like stopping, I don't feel like editing, I don't feel like doing any of that. I just want to keep on going, so I'm going to do that. So let's talk about breadth first search. Breadth first search is different than depth first search because we are not going to use recursion. Breadth first search, well, if you'll notice, we kind of imply what it's going to be, right? So depth implied that I went down each individual trail as I went until I couldn't go any further, and then I started going back. So that recursive trail led me down each leaf, or I wouldn't call it a leaf, that's too similar to each branch, essentially. Don't think this is a tree, it's not a tree, but each essential branch of vertexes or vertices are being visited at a time, and we're not kind of making a wide traversal. We're going down one branch at a time and then kind of falling back and going down the next branch. So the pattern is pretty obvious. Breadth first search is pretty much the opposite. We're going to start with the same node here, but we are going to actually traverse it in such a way that we essentially spread out, kind of like tree branches, or like right? Dragon's breath, if you think about it like that, or anything that spreads out, like spill water on the ground and you'll see that it pools out, it spreads outward. That is exactly what breadth first search is. So we're not going to travel all the way from B down to I before coming back. We're going to actually visit each one of the nodes in order that we visit them, and then their respective neighbors, or vertices connected by edges. So let's take a look at the code first. So I'm going to do something similar I did with my recursive call, but now this is not a recursive method, so I don't need to pass it as an argument. I'm simply just going to create a set of visited vertices here within the method. I'm also going to create a queue. Now, ignore this. This is just as standard. A deck is the preferred way to implement a queue in terms of the compile time type on the left. It has all of the same functions that a queue has, but it also has functions for adding to essentially to either end of the queue. For the purpose of this video, I'm only going to use this deck as a queue. So I'm just going to call it queue from now on. I'm not ever going to add to the front. Everything gets added to the back, and it behaves exactly like a queue should. If you're not familiar with queues in terms of computer science and data structures, just think of it just like the line at the local grocery store, or really any time that you get in a line. You get in at the back, and you wait your turn until you pop off the front. So initially, I'm going to add one thing to the queue, which is my start vertex, and then I'm also going to add that to my list of visited nodes. Even though I haven't visited it yet, you'll see why I do it that way. So then we begin a loop, and this loop here will take us through the entire tree. It's going to say while this queue isn't empty, which I have added one node to it, so it is not empty, we're going to pop off that top item off of the queue, and we're going to store it as a reference to a vertex called current. Current will point to a given vertex. Throughout each iteration of this loop, it will point to a different vertex. What we're going to do is first visit that vertex by printing out the data to the screen, and then we're going to get the edges in the same way we did for the recursive call. We're going to get a list of all of the edges, but the difference is now we're going to go through each edge, creating a reference to a vertex called next, the same way I did in the previous traversal. And I'm going to check to make sure it doesn't already contain that node, but now I'm going to add it to the queue. So essentially what this does is it's going to make sure that C, D, and E from B are all added to the queue before any further traversal happens. All of those three nodes are going to be added to the queue and then added to our list of visited nodes, even though we haven't visited it yet. Well, I'll demonstrate. So essentially, once every edge that is contained within the list of edges for the current node has been exhausted or added to the queue, then we are going to essentially drop it, forget about it, and move on to the next one, which will be the top of the queue. So how is this going to work? Let's step through the illustration first. So A is added to our queue. It's added to our our initial list of items to visit. Then A is popped off with this first step, queue.pull. It's referred to as our current node, and then we're going to go through each one of its edges and add those edges to the queue, namely B. Now B will do the very same thing. It's going to add C, D, and E to the queue. Now I've represented them with these fancy pink lines. I know, don't be too impressed. It was really, really difficult to do that. Not really, it's MS Paint. But essentially I've added these 3 items to the queue. I visited B, so I'm done with B. I can forget about it. I'm going to move on. I'm going to pop off the first item in the queue. Well, I went ahead and I added them in the same order I did in the last video. Well, really they came off the list in the same way they came off the list in the previous example. So we know that we're going to visit C first. So we visit C. Now, before anything happens, before any further traversal happens, I'm going to add everything from C into the queue. So we know we're going to add H. I didn't mean for that red line to get painted there quite yet, so I apologize for that. But I can basically, as you can hopefully make the assumption now, you'll notice that H got added to the queue, but it got added to the back of the queue. So even though it was technically the next node to visit, or you might think it was the next node to visit, D and E were still ahead of H in terms of the line. So H is tentatively in the queue, but it hasn't yet been visited. It's been added to our list of visited nodes because we know it's going to be visited, but it has not yet actually been processed. So we're going to go ahead and process D. Now D is going to add both F and G into the queue, but as we know, those are not next either, and neither is H. We still have to visit E. So as I step forward, you'll see where the term breadth first search comes from. We are expanding out in a breadth fashion, not depth, but breadth. So as we add each individual edge's target node or vertex to the queue, they are visited in that same order. So now E will add the edge to K, or K itself, to the queue, and now we know that the order that we added these in was C, F, G, and K. So we're going to go ahead and visit, sorry, I said C, F, G, and K. I meant H, F, G, and K. So now I'm going to go ahead and visit H because it's going to be the top of the queue. H is going to add it would add the vertex F to the queue, but what do we know about that vertex? It's already been contained, so we're going to ignore it, hence the purple. Just go with me here. Now we know that F is actually the next in the queue, not because H said to visit it, but in fact H didn't. H said, well, I don't have any to add to the queue because F's already in the queue, so I'm just going to print my stuff to the screen and move on. So now we're going to pop off the next item in the queue, which is in fact F. F will add its neighbor I to the queue, and it will terminate. That iteration will stop, and we're going to continue on to the next item in the queue, which is G. G is going to get visited. G is going to add its neighbor to the queue, which is J. Then K is going to get visited from E. K is going to add, K is going to attempt to add its neighbor J into the queue, but we're going to see that J is already in the queue, so again, we're going to skip it. Now we have 2 items left in the queue still. I will get visited, and J will get visited. So we should expect to see, when I print this step to the queue, or to the screen, A, B, C, D, E, A, B, C, D, E, H, F, G, K, H, F, G, K, and then I, J. I, J. So, exactly as we anticipated. Let's go ahead and watch this happen. Yep, okay. So, let's create a new list, which is empty, of all of our visited nodes. Let's create a new queue, which is currently empty. Let's add 1 item to the queue. If I look at the first item in the queue, it is this item with data A. Exactly as we would anticipate, we're going to add that to our list of visited vertices, and we're going to say, hey, while the queue is not empty. Well, guess what? Queue's not empty. We got one item. Let's actually make this fit the screen a little more, even though it kind of ruins my debugging window. There we go. Okay. So the current item is going to be the first item in the queue, which is the item with data value A. We're going to go ahead and we printed it to the screen. We're going to go ahead and go through each one of its edges and add them all to the queue. So if we haven't already visited it, let's add it to the queue, add it to the visited, and that's the only edge. So we're falling back to if queue is not empty. Well, we know it's not empty. It's got one item, and that is item with data value B. So let's take that off, store it as current. Current has data value B. We're going to go through the list of edges for each edge. Let's add it. Let's get the 2 vertex that we're going to be going towards. Let's make sure we haven't already visited that edge. So next is data value C. We're going to go ahead and add that to the queue, add it to visited, go to the next edge. Now next is data value D, as we expect. And so we're going to add that to the queue, add that to visited, and then the next edge will be data value E. So add all 3 of those to the queue, and then we're done with all of the edges so we're back to while queue is not empty at this stage. So now we're going to pull off the top item off of the queue, which is going to be current with data value C. We'll print that to the console, ABC, as you can tell. We're going to go through each edge. We're going to add that edge to the queue. So I'll show you that next is the current edge we're looking at, data value H, which is right here. So add H to the queue, add it to our visited list, and then we're going to fall back to while queue is not empty, because C only has one neighbor. As we advance here, we're going to pull off the top item on the queue, which is where's current? Oh, yeah, scroll down. Current is the one with data value D, as we expected. D is going to get visited, printed to the screen. We're going to go through each one of its edges and add them one at a time to the queue. So as you can see, the next edge is one of value F. Let's add that to the queue, add that to visited. The next edge is the one with data value G, F and G from D. So we're going to add that to the queue, add it to our visited, and then we're done with all of the edges in edges for that node. So we are at this step. Now we're going to pop out the top item off the queue. It is the vertex with data value E, right here. Then we're going to print it to the screen, print E. We're going to get all of its edges. It only has one. It is the one with data value K. And we're going to add it to the queue, add it to our visited. Now we're here. So then we're done with that. So we're going to go back. We're going to pop the top item off the queue. It is the one with data value H down here. We're going to visit it. Then we're going to go through each one of its edges. The next edge is the one with data value F. We've already visited F, so you can see here it's going to say visited.contains next. It does, so we're going to skip adding it to the queue and go back. Well, that's the only edge, so we're back to pulling off the next item off the queue. The next item on the queue is the one with data value F, so we are here. We are going to print it to the screen. We are going to go through each one of its edges. It only has one edge. It is the one with data value I. It's going to add that to the queue. It's going to add it to visited because we haven't already visited it. And then we are going to go back to pop off the next item off the queue. The next item on the queue is the one with data value G. So we're right here. Then we're going to print it to the screen. We're going to go through each one of its edges. We're going to get, there's only one, data value J, right here. Visit G, add J to the queue, that's what we're doing. Go back to the top. Pop off the next item off the queue. You see this is getting really, really repetitive. The one with data value K is our next one to be visited. So we're going to go ahead and do that. We're going to print it to the screen. You can see K is being printed there. Then we're going to go through each one of its edges, which has exactly one, and it is the one of data value J. You're going to see that it's going to say, hey, visited, do I contain J? And I do, so it skips that line. So we have ignored that path to J. Pop off the next item off the queue. We're almost done. one with data value I. It's going to get printed to the screen as we visit it. Go through each one of its edges. It does not have any, so it fell right back off. And now if I look at my queue, you'll see it only has one item left. We know it's the item here, so we're going to go ahead and pop that item off. Now our queue is empty, but we're not done yet. Current data has value J, which is this one right here. Let's print it to the screen. Bam, we visited that node. Now we are going to go through each one of its edges, which it does not have any, so that loop will terminate or won't even initialize. And then while queue is empty, well, the queue is empty. Or while queue is empty, or the queue is not empty, but the queue is empty. So we're going to go ahead and finish that, and that is the end of our breadth first search. So to add another line in here, I'll just do it a couple times so we can see the differences. So we did both depth first and breadth first, and you saw exactly how both of those processes went. You'll see that there are some similar elements, A, B, C, in that order, but they aren't going to be visited in the same order. And there's different reasons why you would do different types of traversals, but these are the two basic ones, depth first and breadth first. And I really hope this video was informative, as it was exhausting for me. I am very, very tired of talking, and I'm going to end here, and most likely tomorrow I will do the video for Dijkstra's algorithm, where we talk about pathfinding from one node to another, and these weights that I've indicated on this graph will come into play during that video. So hopefully by the time you're watching this, you can just say, huh, nuts to you being in the real world, and you can just click on the very next video if you still have the energy after watching all of this. So thank you very much for tuning in. It is always a pleasure, and I will see you next time.